Basin. We're now going to talk about hotspots. So first thing you notice if you look at the Pacific Basin is one that it is freaking huge. The Pacific Ocean literally covers about half the planet's surface. This is kind of home of the whopper as far as ocean goes. The other thing you'll notice is just that you don't see a lot of plate boundaries, at least if you're in the heart of the Pacific. You have this one running through the Eastern Pacific, or East Pacific Rise, a rapid spreading ridge. And then you have a little trench here. We have a somewhat convergent, somewhat transformed boundary over here. But out here in the middle of the ocean, there's just simply no sort of plate boundaries. We do see, however, is a bunch of islands. We're going to talk about how those islands get there, and also how you get volcanoes in the middle of a landmass far away from any plate boundary. What we're going to be looking at is known as hotspots. Hotspots, and this will be the final part of our plate tectonics lecture. So we're going to zoom in to a chain of islands known as the Tahitian archipelago. So many people have heard of Tahiti. It's certainly a popular vacation destination, as well as Moorea and some of the other surrounding islands of French Polynesia. We're actually going to start a little bit south and east of there. And yes, sir. So one of the cool things you notice if you look at rock dates for the French Polynesia is that the islands tend to get progressively older in one single direction. So we'll start with the youngest island. It's actually just a little bit south and east of Tahiti. And your older islands are over towards the northwest end. Younger, and that the direction of plate motion is generally understood, of absolute plate motion is generally understood to be towards the northwest. Now, the cool thing is, not only do the islands get older, but you see very common landforms on each of these islands, unique to the age of how recently they erupted. We're going to start with Mahitia. Let's start with Mahitia here, youngest of the ones. Then we're going to move, and then you're going to see that they get older in the direction of plate motion. That's the first thing you notice about Mahitia is that's very young. It doesn't have, it's a very fresh volcanic edifice. And it's being battered by waves. There hasn't even been time for coral. It has these beautiful sort of black sand beaches. So what you're looking at underneath Mahitia is the following: 5, 4, 3, 2, 1, action. So it creates these features like Mahitia or Hawaii is you get a plume of hot molten material. Now, the reason I put this in quotes is the origins of these things, how often, where they come from is still up for debate. While we have identified them in places like the Hawaiian island chain, a lot about them remains unknown, even for the ones that are the best studied. So you have this sort of plume coming up against the surface that starts to melt your mantle. Starts to melt a bit of the bottom of your mantle here. What that'll lead to is material coming up, and eventually you're getting this a hotspot volcano at the surface. These tend to be very run eruptions because there's not a lot of gas here. And you get these beautiful volcanic islands in the sea. Now what we're going to do is look at 4, 3, 2, 1. So as I head towards the island of Tahiti, what you notice is you still have a conical shaped peak, but your volcanic peak's going to be a little bit broader, and it's going to be a little bit more eroded. Older eroded volcanoes, no longer producing lava or hasn't done so in a while. And in the case of Tahiti, the original volcano is going to look a little something like so. So your original volcanic rocks are still present, but they start popping up along the waterline. This, by the way, is zoomed in quite a bit. It's been eroded around the peak. And what's happened is you're now starting to see some coral reefs pop up along the edges of your island. We're going to call these frigging reefs because if you're a pirate who plans on stashing your all the loot you pillaged and you run aground on the island and you run aground on one of these things not too far off the shore, the thing you're going to say is, ah! Now as you move further, 5, 4, 3, 2, 1, action. Now as you move further in the direction of plate motion, you get older and older islands and the reefs get further and further away. And what this is reflecting is that as you move away from the center of volcanism, your island is get less heat. Your crust and lithosphere are colder, and they're starting to sink back in the ocean, and erosion's taking over. And the only thing that's keeping this island in existence is the growth of the reef. So we have over here is and the reef's going to get further away until finally you have almost no island at all. And then finally, you get to these islands where the entire island is the reef and your central peak has been long buried. Now, the term we have for these is we call them atolls. 2, 1, action. So we're going to take a look at Hawaii, which is sort of the poster child for this whole principle. Now, one of the things you're going to read in your textbook, and I'm going to tell you your text is not quite right on this. So one of the controversies is, first of all, you notice how Hawaii definitely has this linear chain of islands, and definitely the Guard Island is much older than the Big Island. In fact, we have active volcanism up here. Even more awesome, we actually have some volcanism taking place just offshore here, and in at some point in our future, we'll have Loihi, that's the one. Yes, we'll have a new island in the archipelago. As you can see also that as we move down the chain, the islands start out very tall. This one is actually, believe it or not, the tallest mountain in the world if you measure it from base to summit. The islands get progressively lower as you move further north and west in the direction of plate motion, and they also get more and more weathered. So you can see this nice linear chain of islands kind of tracking the plate that seems to track the plate motion for a long way. And then suddenly this chain, and they get lower and lower and more buried. And then suddenly this chain makes this abrupt bend. Now, the old thinking on this was that your plume was perfectly stationary. And so the hypothesis went that you had your plate moving basically roughly like so. And at some moment in time, it suddenly shifted and started moving like this. We now know that to be a load of crap. You'll get to look at that in some of your reading. So the one other thing I want to show you about hotspots is what hotspots look on land. And to find what hotspot tracks look on land, like on land, you have to go to one of our favorite spots. Oh yeah, northwestern Wyoming, Yellowstone. So here's Yellowstone, our big classic hotspot. And you can see a couple really neat things on this image. So we have Yellowstone, which is all this volcanic rock. But then if you look closely, you see a couple other sort of circular features, and some of the stuff even looks like dark lava. Yes, these are old lava flows. So here, we're gonna turn this on its side to create a little cross section, and I'll describe it, and then we'll wrap up of this part of the lecture. So just like in your oceanic crust hotspot, you're getting some sort of rising plume of hot material, something that is causing that lower bit of the lithosphere to start to generate some kind of melt. And that melt is making its way up like so. It's starting to melt the crust, and you're getting magma pooling right over here. Now, you might notice Yellowstone looks a little different from the ones you see in the ocean. That's because this is continental crust. There's a lot of water in it. It's also a little bit thicker. It's a little bit harder, but every now and then, every few tens of thousands, hundreds of thousands of years, you get all this gas and and that also means there's water in here, will periodically heat up, and you'll get some of the biggest explosive volcanic eruptions that are seen anywhere. Now, there's a small chance this would happen in our lifetime. Unlikely. And if it did, it would definitely make things very different. Now, what you're seeing over here is you're seeing progressively older magma bodies associated with the same process, like so, because again, your direction of plate movement is like so. Now, in this case, this shows some evidence that the direction, the relative motion between the hotspot and the North American plate has changed a bit. And this is sort of cool. So that about wraps up all the things I want to talk about with hotspots and wraps up our plate tectonics module. Be sure to take the quiz.